So first we remind ourselves that for a single electron in a magnetic field, the energy levels, if the electron is confined in 2 dimensions, is completely quantized, and the distance between Landau level is equal to EB over m. We can consider the limit in which this energy scale is much larger than the energy scale that is associated with the interaction. So one very naive way to think about this problem is that interaction is going to split the complete degeneracy of the Landau level. Of course, it's only in it's not in the real world. We cannot talk about the single state eigenfunctions when the theory is interacting. But roughly speaking, we have a degeneracy splitting, which is equal by the order of magnitude to E squared divided by R. We think about electrons as particle, and R is the distance between one electron and its neighbor. And one can convince ourselves that if we take the magnetic field going to infinity and keep the filling fraction finite, then we will have E squared over R to be much smaller than EB over M. Basically, this one grows like linear power of B, and this is only a quadratic root of B. This is how one can imagine the lowest Landau level limit to be. One can take this lowest Landau level limit in experiments. Since I'm a theorist, I'm going to think about the lowest Landau level limit slightly differently. I'm going to take M goes to 0, keeping the magnetic field fixed and the filling factor fixed, keeping V fixed and the filling factor is fixed. In this case, EB divided by M goes to infinity, and I'm left with a single Landau level. So that is how I'm going to think about the lowest Landau level limit. As you will see, it will be useful a little bit later on. Now, in the lowest Landau level limit, the problem becomes, as Janendra told us, kinetic energy is completely frozen. So effectively, in the lowest Landau level limit, the problem becomes that of a Hamiltonian that is only a sum of the potential energy V. In fact, it's actually V tilde times R A minus RB. Okay. A and B's are pair of indices that should not equal to each other, and both run from 1 to n. So only the potential energy. So V tilde is slightly different from V. After the projection to the lowest Landau level, there is a small change in the interaction. And R here is the guiding center coordinate. So the guiding center coordinate is defined this way. So Rx is equal x plus LB squared times 3y, and Ry is y minus LB squared kx. So using this occasion, I'm introducing the magnetic length. The square of it is equal to 1 over EB. And this k is the gauge invariant momenta. So the guiding centers physically is the if I think about the trajectory of an electron, of a classical electrons, the classical electron move in a circular orbit, and the center of that circular orbit is the guiding center. And the Hamiltonian now becomes, in the lowest Landau level limit, is a function of the guiding center. And the properties of the guiding center is that for a given particle, the two guiding center coordinates do not commute with each other. It's equal to I times LB squared. So one can make an analogy to X and P in quantum mechanics. So X and P in quantum mechanics commute to IH bar. Okay. The Lewis-Landau level problem is similar to the problem of particles that are in space. So the X coordinates is conjugate to the Y coordinates. The Hamiltonian is a sum of potential energy of the interaction. And this is a problem that Janendra mentioned in his talk to be one of the most difficult problems because we don't have any small parameters in the theory. Everything is of order 1. So now suppose I'm writing down the equation of motion of this system. So the equation of motion would look something like this: R A transform 1 to N dot I. So this I is X and Y coordinates, is equal, supposed to be following the rule of quantum mechanics, minus I, the commutator of R A I with the Hamiltonian. And the Hamiltonian is known. And so you can do the calculation very easily. You find the following. It's epsilon ij up to a sign. I'm not sure I have the sign right here. Sum over all b d over d r a j v of r a minus r b. So this is the equation of motion. You can see it's what is written here. If I'm trying to interpret this equation as an equation of motion of a system of classical particles, what I have here, this is a force acting on the particle A, right? This derivative of the potential is the force. So what I have to do in this equation is the following. First of all, I compute the force acting on this particle A.
Yeah, I mean, what's the prescription for the ordering?
The prescription for the ordering is a little bit subtle, so let me write it here. So this, when I write V of R, what I have in mind is integral over dq of V of Q and E of IQ of R. Okay, and here the ordering is pretty obvious. I just write it in Taylor series. And then in each Taylor series, I just expand this.
Good.
You don't have to symmetrize it. The Q dot R is just commuted itself. And so you just, so that is it. So that's why here, there is a unique way to do that. But now I'm thinking about this problem as a classical problem. Here I have a system of particles interacting with potential. Normally, we have to compute the force acting on the particle A, and then use Newton's law, F equal ma. You get the acceleration. But here, the equation of motion is completely first order. That means that if from all these particles we get the net force acting on the particle A, so let's call that F of A. Then the particle A will move in the direction perpendicular to the force. So that's how it's the equation of motion will tell us. So it's a very, even from the point of view of classical mechanics, this is a strange problem. In mathematics, there is a name for this problem, namely, well, for one particular case, when V, so it's when V of R is proportional to logarithm of R. This problem is called in mathematics is called, sometimes called the n-vortex problem. And in mathematics, usually the motivation to consider this n-vortex problem is from the theory of two-dimensional turbulence. Onsager speculated in the end of 1940s that in two-dimensional turbulence, In some sense, this describes the motion of vortices in a two-dimensional fluid. And this problem might help explain some features of two-dimensional turbulence. But here in quantum Hall physics, we have to deal with the quantum version of this problem. We cannot just have a classical problem, particle moving with this law, but we have to quantize the whole Hamiltonian. However, by looking at this equation of motion, I can motivate some further peculiarities of the quantum Hall problem. Namely, there is the following things that you can check. These are the conservation laws. So the conservation laws, the first conservation law is trivial, that the number of particles is completely unchanged. So that's just by definition. Second conservation law that we have is the conservation of the sum of the coordinates of all the particles. Okay, so let's see. If I have two particles, two of these interacting with a force, a central force, that is a force acting on that particles A and particle B are opposite to each other, then the velocity will be also of the motion of the particle will be opposite. So the center of mass of these two particles will remain in place. So you can check that the these operators, sum over A, is commute with H, with the Hamiltonian. In fact, because Rx and Ry commute to a number, one coordinate is a momentum with respect to the other. And so actually R itself is an operator of translation. This is not just any operator, but this generate translation. That is, it shift all the R to R plus alpha by the same amount. And the translational symmetry of our potential energy means that this operator commute with the Hamiltonian, so is conserved. So this is one conservation law peculiar to the Lewis-Landau level problem. Another conservation law is d over dt, sum of R A squared. That can also be shown to be equal to 0. Okay, so again, you can check that this operator, sum over A of R squared, generate rotation. And on the Lewis-Landau level limit, this can be thought of as the total angular momentum. Angular momentum is conserved if the potential energy depends only on the absolute value of the difference in the coordinates, but not on the direction of the Ra minus Rb. And so on the Lewis-Landau level, there is very peculiar, strange, unusual conservation laws, which one can try to write in the local form. So if I introduce the density of charge, so this density of particle numbers, how many particles is in a volume, sum over delta x minus xa, usually. Then the conservation laws becomes d over dt, integral of dx, rho of x is equal to 0, d over dt, integral dx, x of rho of x is equal to 0, x squared. So here is the scalar x squared. rho of x is equal to 0. So three conservation laws, which can be motivated by the equation. This can be shown explicitly from the equation of motion of particle on the lowest lambda. X is, so you have a two-dimensional system. Rho is a function of x and y, right? So rho is the density of particle in a place that has the coordinates x. So that's why x is a vector. This integral is over two-dimensional x, and there are four of these conservation laws. One here, two here, and one here. Okay, one component. This one has two components. So that brings very interesting questions. Usually we are used to conservation laws that comes from some symmetries of the problem. So for example, the conservation of charge is related to gauge symmetry. The conservation of momentum is due to translational. Conservation of angular momentums related to the rotational symmetry. But somehow these symmetries are all involve the same density. How can a theory, if we want to construct, for example, an effective field theory, quantum field theory of the quantum Hall effect, how do we guarantee, how do we make sure that these symmetries are satisfied? What kind of gauge principle has to be imposed in order for this symmetry to remain? So the question here is there any gauge symmetry? So this would be some kind of a U1 gauge symmetry, but how about the other ones? Is there any way one can interpret that as gauge symmetry? So let's look at these conservation laws a little bit in a slightly different from a different point of view. But before that, is there any questions so far? Yes. So here I'm a little bit fuzzy about this. So this x is the real. Well, you can show that it's actually x is it. You can show that this is valid when rho is the true density of the electrons. That is. Okay, so we will see now how to think about these conservation laws in a local form, and that would be partially a question answer to your question. So usually the conservation of particle number can be written in a local form like this: d rho plus dt plus gradient of j is equal to 0. J is the particle number flux. Now I'm going to write the second equation. Now this equation, let me first write it down and then explain. Okay, so what I've written here, and what I'm written here is the balance of momentum or momentum conservation equation. J is the current, but m times j is the momentum density. Right? If I have a system with Galilean invariance, then the current and the momentum density is proportional to each other. So here's the conservation or the continuity equation for the momentum. if I take a small volume and I count the balance of momentum, so the T over dj comes, the change of momentum comes from this is basically the forces coming from the stress tensor. Tij is the stress tensor. The diagonal elements can be thought of as a pressure. So that is the forces that act on the edge of this volume. And this here is the Lorentz force, which has to be taken into account because we have a non-zero magnetic field. Any question about this equation? Conservation of momentum.
It's cutting you that constant and it was a 0.
I'm going to do it now. Right. M equal to 0 means this. And is M equal to 0. Momentum disappear. The term with momentum disappear. So J cross B, by the way, here I'm in 2 dimensions. So J cross B is just a number. B, it's a vector. B is along the Z direction, but J is along the X and Y direction. Now this equation, which remains, can be solved for J. And the solution is that J, let me say, how do I say that? So let me write it in components. Up to a plus or minus sign, epsilon I j p k t k j, something like this. Up to a sign, you can check. This is equation. And then one can put it into these equations. And the equation of conservation of charge can be now written a different way, plus di dj jij equal to 0, where jij is up to something of order 1, a sign, I think, up to a sign is here, epsilon I k t k j plus epsilon j e k I. So here's the consequence of the 2 conservation laws when we take m goes to 0 in it. So it should be valid on the lowest Landau level. On the lowest Landau level, the continuity equation becomes second order in spatial derivative, from which you can check that integral of dx rho is equal to 0, but also integral of dx x time rho is also equal to 0 because it's integral, following the equation of motion, integral of x time dB of j. I'm just dropping all the indices. By integration by part, you can put all this derivative acting on x, and then you get 0.
The stress tensor here is sort of this explained. Doesn't include the what can be it.
It is the stress tensor of matter. It's not, so
Nothing E in this test one.
well, the total, the stress, will be that. So I'm treating my field as a background. There is no Maxwell equation. If I have if I include also the Maxwell equation, then the total momentum of the whole system is going to be conserved. But it's not what I'm interested in. So it's only matter, the electronic part of the stress tensors. And you can also show that d over dt of dx x square rho is equal integral of jii over dx up to a sign. And this jii is equal to 0. This jii from here, let's show that it's equal to 0. And so everything that we have seen from the equation of motion is also reproduced by this very simple manipulation of the conservation laws of the continuity equation.
The method,
there are this equation now in general cannot be
we have
density. Yeah, we have density conservation, right? Yeah, but then there is this equation that constrain the momentum. This momentum is, we cannot solve the second equation. Then none. So m equal to 0 simplifies the discussion. Yes. M equal to 0. This is an approximate symmetry. The symmetry is here, but it's also a link. Well, basically, you have to be able to ignore this term compared to this term. Right? Basically, whenever energy scale is smaller than the cyclotron frequency, and you can ignore this. M goes to 0 means that we take the lowest Landau. I'm taking the lowest Landau level limit, and m goes to 0. It's a very clean way to take the lowest Landau level limit when the distance between the lowest Landau level to the next Landau level goes to infinity. That's how I cut the lowest Landau level limit. So now we are going to try to encode this symmetry. So this is how we should strive for. We want to understand the three conservation laws based on some gauge principle. And from this discussion, it's clear that it has to do somehow with the stress, because here Jij is related to the stress tensor. We should think about some coupling to gravity, coupling to the metric. The symmetries that we want to expose will come naturally if we try to couple the system to the external metric. So this conservation law here is going to be something that knows about coupling of the system to gauge field and to the metric. It's some kind of a hybrid. Yeah, trying to get some kind of hybrid gauge principle. Any question? So let's try to do that. So how I'm going to couple. So I'm going to try to couple the theory to. So I'm going to couple theory to spatial metric. Let's call that Gij X, and try to see what symmetry that I get. So in general relativity, we know that coupling this, if we have, well, this, let's recall Einstein's principle of equivalence. So in Einstein general theory of relativity, there is an invariance with respect to, so in Einstein theory, we have invariant with respect to changing all the space-time coordinates. I can parameterize, use any coordinate system in space-time. Now in the quantum Hall problem, it's not a very useful symmetry because we have a non-relativistic system. So it's time is better, well, it's more convenient to consider time it's absolute. So we are not going to change time. We are going to require that under gauge transformation, time remains the same. reasonable. I'm going to change only space. X, go to x prime. It's a function of x. Fine. But we also recall that our system lives in a magnetic field. It's a two-dimensional system in a constant magnetic field, B. And if we have a constant magnetic field, in order for the field to remain constant, we require that the determinants of the Jacobians that take us from one system to another system is 1. Please. So basically, the picture is that we have a diffeomorphism that map one volume, say, in another coordinate system. It may be a different volumes. But in order for the total magnetic flux through that volume to be fixed, we require that the coordinate transformation do not change. That it has a unit Jacobian. So that's the symmetry that we want to impose. We want to impose a symmetry with respect to area preserving diffeomorphism. So area preserving diffeomorphism are the following. The small symmetry transformation looks like x, I, so that means just write in components, going to xi prime equal xi plus psi of I, where derivative of psi is equal to 0. Divergence of psi is equal to 0. That is the area preserving bits. What? Fine. Any question so far? So this psi is can be a function of space, but can also be a function of time. And to allow for a transformation that depends on both space and time. So if this is 0, then I can solve this equation and write in 2 dimensions psi I j e j of lambda. Lambda is also a function of space and time. So if I require that the theory has symmetry that is parameterized by one function, then I expect there is one conservation law. Let's recall. So in the usual case, if I require the theory to be invariant under gauge transformation like this, then I get the transformation, I get the one of the what identity is the conservation of current. So now I'm going to, well, one can expect this gauge invariance leads to one conservation law. And perhaps that conservation law is the d of 0 over dt plus di dj, jij is equal to 0. So that's a goal, to get from this gauge invariance the conservation law that we have seen in another way. Any questions so far? No. Okay. Although let's before going on, this list of transformation, this include non-trivial one, for example, Galilean boost plus PT, example. That will be part of the of this transformation. Okay, so how does under area preserving diff, how do a mu, the questions Gij transform? Okay, this is the question that in order to figure it out, we just need to know how different kind of tensor transform under general coordinate transformation. Okay, so for Gij, transformation law is very easy to figure out. Let me write it down only at the linearized level. So Gij, external metric, become Gij minus Eixij minus Ejxi. And it means if I write Gij equal delta Ij plus Hij, H is much smaller than 1. I'm going to do only thinking about metric that are slightly different from the flat matrix. And Hij is going to be go to Hij minus this, so it's up to a constant. It would be epsilon I k dk ei ej lambda plus epsilon jk dk ei lambda, up to some sign ignoring here. So here I put this into this equation, and I get the transformation law for my metric. But then I have to figure out how A0 and AI transform. Okay, so here is the thing that we have said. We restricted ourselves to only area preserving diffeomorphism. So that means that the magnetic field remains constant under this. Whatever I do with AI, D1A2 B equal D1A2 minus D2A1 has to remain constant, goes to be 0. That's by design. I don't want to change the magnetic field. And so this AI, whatever it's the special components under transformation, all that it can do is it can undergo gauge transformation. So it's going to be AI prime, which is some kind of AI plus DI alpha. Okay. So using that, I'm going to combine this area preserving diff with gauge transformation and leave AI unchanged. So I'm going to do gauge transformation after doing my calculation, which I'm not doing here because it's a little bit long, but you can do the explicit calculations and convince yourself that under area preserving diff, AI can be made unchanged by combining it with the gauge transformation. And now A0 is I'm going to present you the final result. A0 is going to be A0 plus lambda dot plus dot dot dot. A term that I'm going to write because it's not very important. I'm going to write in very little letter DIA0 J lambda. It's some coefficient. So what we have achieved? We have achieved a formulation of the symmetry of the fractional quantum Hall problem. The problem now has a symmetry under which the gauge field that change are the zero component of the electromagnetic field and the metric.
So maybe it's maybe well in other some sections relate to the large more tourists.
Yeah, it's I haven't thought how it means. Maybe we can discuss that because I suspect there is some interesting things that one can say. For example, if I work on a torus, I can let C to be not yeah, that's can be a linear function. Yeah.
So now the thought should be the electric field. It's just like boosting the play. The southern coming at you is boosting frame that you got what? But that's available.
Yeah. You can say the following. Suppose I'm making this Galilean boost. So in order to get this Galilean boost, I have to take C to be equal to Vt, which means my lambda is a linear function of space, and as function of time. It's a linear function of both space and time, and that leads to A0 that is a linear function of space, which is a constant electric field. So a boost generates a constant electric field. So that's all in here, one of the examples. But we have a full gauge version of the symmetry, and you can now check that this combination of these two leads to the word identity that follows from this is the conservation laws that we have derived. So if we have, let's recall, if we have the partition function of the theory, so let's call that log z as a function of A0, AI, and Gij. And we know that it's invariant under this transformation. Let's call that lambda dot. AI remains the same, but Gij becomes Gij plus this di. dd gets epsilon I j k lambda epsilon j k di dk lambda is equal to 0. I'm sorry, is this log z doesn't change. Then if I define the current to be derivative of log z with respect to A0, Tij is the derivative of log z with respect to Gij, I get the word identity that comes from this is going to be d over dt of rho plus derivative of epsilon ik dj dk of Tij plus Ti ik plus I goes to j equal to 0. So we have been able to encode the conservation laws in the form of symmetry. Okay, so that's good. Did I cheat too? Was there a cheat? I think there is a story about, I think, Althusser, when he give a talk, he usually asks whether there is, if there is no, he said, if there is no cheating, that it would be mathematics, not physics.
Yeah.
And so the thing that I slightly cheated here is that this actually, in order to argue that this kind of symmetry is valid or a system, I actually assume m goes to 0. I'm going to leave you where that m goes to 0 limit has been taken. So only in m goes to 0 limit, I can guarantee that this kind of thing, this kind of argument works. Okay, so now, any questions so far? For symmetry, it's good with symmetry. Now I'm going to try to, I'm going to discuss consequence or effective field theory. But this will be effective field theory that is not very commonly taught in fractional quantum Hall effect, because it's an effective field theory that captures gravitational response. Okay, so, but this does capture some physical effect, something that I'm going to explain. The Hall viscosity. It's going to capture another thing called the shift, when it's due to when in z, and it's going to relate these two together. And I'm going to, well, to advertise, I'm going to at some point explain the Haldane, I call the Haldane bound. But that's maybe in the next lecture. Okay, so we want to understand how to describe the gravitational response of a gap system. Let's assume that the theory is gapped. The ground state is gapped. A gap system means that I have an energy scale at gap delta. And I would like to understand how to describe the energy that are much smaller than delta. So when energy is much smaller than delta, there is no dynamic degrees of freedom. Right? Or the everything that the low energy physics looks like trivial. But we know from condensed matter physics that sometimes a gap state can have very non-trivial response to external field. For example, one example again is that quantum Hall effect. So quantum fractional quantum Hall, or just any quantum Hall system, there is a gap, but at low energies, the dynamics, the response of the system can be captured by the Chern-Simons action. The S response to electromagnetic field is captured by some integral dx, epsilon f mu nu lambda, a mu d mu a lambda, with some coefficient. And the way that one used this action, which has no dynamic degrees of freedom at all, just the external field, is that we say the current, electromagnetic current, is the derivative of the action with respect to a mu. And that's that coefficient times epsilon mu u lambda d mu a lambda. And from that we can identify this with the Hall viscosity, Hall conductivity. The Chern-Simons term encode the response of the system, fractional quantum Hall system, to external electromagnetic field. Okay, so we want to do the same thing, but for the response of the system to an external gravitational field. Right, to see what we can write down that has this gauge symmetry. So what is the requirement? So the requirement is that we have an action. Okay. Now I'm going to include in the action only the A0 and Gij. Okay, so because AI, under my transformation, AI doesn't change. I combine area preserving deep with gauge symmetry, so AI doesn't change. So I exclude AI from the magnetic field is not something that I'm going to probe. I'm going to probe on the density. I get a probe, a density, that one coupled to the density, and this one coupled to the stress tensor. So there's only gravitational probe and the probe of the density. Okay, I'm going to work at the quadratic level also to simplify the calculation. So this S is invariant under the following transformation. A0 goes to A0 plus lambda dot. Okay, and another one. Hij go to Hij plus, let me write, epsilon ik dk J lambda plus epsilon jk k di lambda. In fact, here I assume magnetic field to be 1, and so the length scale, the length is measured in unit of the magnetic length. So it's slightly more complicated gauge symmetry than the U1 gauge symmetry, but there is a name for this. Actually, it's called Higher-end symmetry, H symmetry. Usually associated with the name Predkov, who introduced it in the context of so-called fractons. These are particles, quasi-particles that cannot move. The notation here is slightly different from what Predkov used. He uses another tensor that called Aij that's related to our Hij by rotation with using the epsilon tensor. Fifth is theory of Predkov is the gauge field A0 and Aij. And you can see that it's a symmetric tensor with a zero trace. And in terms of Hij, in terms of Aij, the gauge transformation on A looks like Aij go to Aij plus Vidj lambda minus the trace. So Predkov's motivation is completely different from fractional quantum Hall effect, but in the fractional quantum Hall effect, the gauge symmetry turned out to be the same. Okay, so now I'm going to write down possible terms that one can. So we need to write down something that has this symmetry, and as usually we don't have the gauge field that carries 2 indices. We have only the gauge field that carries 1 index. Usually that the story would be A0 and AI combined into one gauge potential. We can write the Lagrangian in terms of electric field and a magnetic field. Introduce F mu mu equal d mu a mu minus mu a mu, right? And the Maxwell action would be E squared minus V squared, etc. Here, the equivalence of the electromagnetic field is that the electric field now has two indices, B0 Aij minus Bi Dj A0, maybe plus some kind of trace part. And we can also write down the magnetic field. Magnetic fields, I'm not going to write it down. But as the usual, in analogy with the electromagnetic case, if you do it like this, we miss important term, important things. That is the Chern-Simons kind of term. It is Chern-Simons. There is a Chern-Simons term, which used to be ADA in the U1 case. Now you have to construct it yourself. I'm going to write down the answer here for you. The Chern-Simons term looks like this. It looks like H0 Bidj Hij plus or minus up to a sign, and figure out the coefficient. Epsilon jk Hik Hjk dot. Then the Chern-Simons term, very easy to show that this one has is symmetric under it's under integration over x. You do integration by part, you get the Lagrangian density is not invariant, but the whole current it is invariant under this transformation. Under this transformation that I've written down up there. Okay, so we are going to interpret this, maybe not today, but next time. This term turned out to be related to something called the Hall viscosity. That is how the system developed an odd response to parity, odd response to gravitational field. We can see it is odd because of the epsilon tensor. Yeah. We change the metric, then we have it's a gravitational version of Hall conductivity. In Hall conductivity, if we turn on an electric field, we have the current in the direction perpendicular to the current. Here, if you turn on something that looks like an electric field, but from the gravity perspective, you get the current, which in this case, the stress tensor in the direction perpendicular to this gravitational electric field. This coefficient turned out to be related to something called the shift. It was introduced by Wen and Zi. And it's the topological properties of quantum Hall state. Basically, the shift is can be obtained by putting the quantum Hall system on a sphere. And then the number of electrons is related to the number of flux quanta through the sphere by formula that is not just Ne equal the filling factor times the number of flux quanta, but there is an offset, and the offset is the shift. And the gauge invariance of this action rely on the fact that these two coefficient is the same. And so the gauge invariance required that the Hall viscosity is proportional to the Wen-Zi shift. Yes.
You just want to first the God you
have a time-dependent
wait.
It's not time-dependent strain. It's time-dependent displacement. That is the how to say. It's the strain is time-dependent. Sorry, you're trying to set up some in a fluid, a flow that's with a constant shear, strain rate, constant strain rate. So it's or viscosity is the stress tensor is perpendicular to the strain rate. Yes.
That's what the about to trade it legally. You write down you was just saying I got that proton off the needle, but I didn't need this up to that. You're only by the you need to get it. What's the degree Irish gap to do it to it?
No, yes. So this so far we have avoided this question because I'm in the fractional quantum Hall effect. I can treat the external field completely as a background field. It doesn't have any degrees of freedom. So it's not these H and these A fields are not dynamical fields. They are just something that we use to probe the system.
So I thought that big when it's on the other and then it's just a kind of it's like and all the data thing says that the best that on the
Yeah, it doesn't require that lowest Landau level. Though the derivation here is simple in the case when we have a lowest Landau level, but it's actually doesn't that if it one can work outside the lowest Landau level. Then yeah.
Well, that's the what I think don't say that so
Yeah, there is another term, the Chern-Simons. There is a Chern-Simons term that has two more derivatives. That as is like when you write like that omega d omega. With omega is some kind of a derivative of H. And there is one more Chern-Simons term that one can write down. But it has two derivatives. Two extra derivative compared to that Chern-Simons term, yeah.
So, how you get the like a thought that start they try yeah you get this out again you get
yeah. So one can derive these terms from the composite fermion picture. Basically, you have to you have this electrons. You couple gravity to these electrons. It's the composite fermion inherit this coupling to gravity. But what is non-trivial is that when you integrate out, when you fill this composite fermion to some number of his lambda levels, you derive the low energy physics. You have to integrate out this physics of the n lowest Landau level, so you can get this term.
okay. I said as we walk so without split. You do usually you can go more boxy. I'm a feel person.
So this can be thought of maybe next time I will mention, but you can think about this metric as the mass tensor of the electrons. So the electrons usually when we write down the first things that I wrote was this action. Okay, I can so one part of the coupling of gravity to the Hamiltonian is through replacing this kinetic term by Gij, like Gipj, divided by 2n. So that can be thought of as the inverse mass tensor 1 over m ij. That is now anisotropic. So this is one way. It's one thing is to think about that. But one can also probe this gravitational coupling by using Raman scattering. Maybe I can sketch out how the Raman scattering experiment can mimic the coupling of the graviton through a fractional quantum Home system.
So you align the both mathematical by taking the last segment of downward. One number take this take the left. You be asked to start to rock it up. Your favorite.
Okay.
Yeah. You see that probably the last day. Because if you deal with that, you with everything that way, and once you're in the most mathematical to find the battle way, I'll stop by what way. So rock it back on God, so sit.
Is it?
And nice thing about this, but I think maybe not nice thing about the architect, the mathematical was spacing. Yeah, it's the way. All you do is in your place, you get actually started thinking.
E square goes to 0 limit. Yeah, and the square goes to 0.
Yeah, but yet, is it ever turned up? You start with the lock commenting again, and then where everything is up to possible, by the yet.
I can, but it's more complicated, as you said. It's not, yeah. Well, not that I've done that, but I can imagine in my head how it can be done.
First things. No.
Oh, thank you.
And